section 2.6, related rates. This topic is about solving equations for related rates problem. So your goals for today is to find related rates, and second goal is to use related rates to solve real-life problems. So, related rates involves differentiation with respect to time using the chain rule. So far, you've been taking the derivative with respect to x. In this particular example, we will be taking the derivative of the volume with respect to time. So, volume of a cylinder is pi r squared h, and the derivative, the rate of change in volume, is the derivative of this with respect to time. Now, if you noticed, there are 1, 2, 3 variables. This is our u, this is our v. We have to use the product rule, but we will be taking the derivative with respect to time. So derivative, the rate of change in volume, v, is dv dt. And that is equal to, using our product rule, u is equal to pi r squared, and v is equal to height. The derivative with respect to time of the radius, so u prime, is 2 pi r dr dt, the rate of change in radius. Now the v prime, will be dh dt, rate of change of height. Now using the product rule, we'll put this together. So it's u prime v, so 2 pi r dr dt times h plus uv prime, which is pi r squared times dh dt. This is the rate of change in volume with respect to time, with rate of change in radius, with the rate of change in height. So the guideline for solving related rates problem is given right here. The very first thing you want to do is draw a picture. You want to write down the known quantities and also the unknown quantity, the quantity that you want to find, and then label the picture. Second thing you want to do is write an equation involving, so you need an equation involving variables for the known rate and rates to be determined. Then using the chain rule, implicitly differentiate both sides with respect to time. The very last thing you want to do is solve the unknown rate by substituting the known quantity and known rates. So here's an example. A ladder 10 feet long rests against a vertical wall. If the bottom of the ladder slides away from the wall at the rate of 1 foot per second, how fast is the top of the ladder sliding down the wall when the bottom of the ladder is 6 feet from the wall? So first thing I'm going to do is draw a picture. So here's the wall, and then I have my ladder leaning against the wall, and here's the ground. So this is a building. I have a building, and there's the wall. And here's the ground with the ladder, and this ladder. So now, here's my known. I'm going to write down my known. And known are, the ladder is 10 feet long, so this is 10 feet long. And it says, if the bottom of the ladder is moving away from the wall at the rate of 1 foot per second, so I'm going to label this x, and that is the rate at which this ladder is moving against the wall. That will be your dx dt because that's how fast it's moving against the wall, and it's going against the wall, so it's positive 1 foot per second. What I want to know is how fast is the top sliding down. I want to know what this is sliding down. I'm going to label this side Y. So the want rate that I'm looking for, the variable that I want to determine, is the rate at which the Y is changing. So I want the rate dy dt. So I want to know how fast the ladder is moving down as it is moving against the wall. And I want to know what is the rate of this top of the ladder moving down, this is going down, when x is equal to 6 feet. So I have my picture. Here's my known rate. Here's the want rate. Now next thing I have to do is find an equation showing the relationship between x and y. So if you notice, this is a right triangle. So the equation that I want will be a Pythagorean theorem. I have x squared plus y squared, and that is equal to 10 feet squared. This is the equation that I'm going to use to differentiate implicitly with respect to time. So the derivative of x squared with respect to time is 2x dx dt plus 2y dy dt, and that is equal to 0, because the derivative of 10 squared is 0. Now what we're going to do is plug in our known rate and known information. So we know that x is equal to 6, and using the Pythagorean theorem, I could find the distance of y when x is equal to 6. So I'm going to plug in 6 squared plus y squared is equal to 100. This is 36. And then I'm going to subtract 36. So then y squared is equal to 64. And then square root of that, so y has to equal 8. So now we know our y, we know our x, we know our dx dt, we're going to solve for dy dt. So let's plug it in. So this will be 2 times 6 times 1, because that's my dx dt, plus 2 times 8 times dy dt is equal to 0. Now we're going to solve for dy dt. So this is 12 plus 16 dy dt is equal to 0. Subtract 12. So then 16 dy dt is equal to negative 12. And then when I divide by 16, the rate of change of the ladder sliding down the wall is negative 3/4 feet per second. And if you notice, it's negative because the distance of y is decreasing as x is increasing. So negative indicates that the rate of change is decreasing at the rate of 3/4 feet per second. So the key terms that you need to look for are, so here's a verbal statement. Velocity of car, after traveling for 1 hour is 50 miles per hour. Mathematical term to represent this is if we let x equals distance traveled, then the velocity of the car after 1 hour, that will be dx dt, is equal to 50 miles per hour at t equals 1. Okay? Another example. Water is being pumped into a swimming pool at a rate of 10 cubic meters per hour Now this can be translated into, let V equals volume of the water in the pool. So then the rate of, so dV dt is equal to 10 cubic meters per hour. Another example would be a gear is revolving at a rate of 25 revolutions per minute, in which one revolution equals 2 pi in radians. So this, we would have an angle, theta, would be the angle of revolution, angle of revolution. So then the rate of 25 revolutions per minute is d theta dt, which is the rate of change, would be 25 times 2 pi, because it's revolutions per 2 pi radians per revolution. So this will be in radians per minute. And last example for key terms would be a population is increasing at a rate of 200 or 2,000 per hour. And if we let x equals number of population, then rate of population dx dt would equal 2,000 populations per hour. And these are the key terms or keywords that you got to look for when you're looking for rate of change. Okay, so velocity, dx dt. Change in volume, dV dt. Change in angle, d theta dt. And then change in rate of population is dx dt. So here's another example. Air is being pumped. Air is being pumped into a a spherical balloon at a rate of 4.5 cubic feet per minute. Find the rate of change of the radius when the radius is 2 feet. Okay, so the very first thing you want to do is draw a picture, a spherical balloon with the radius here. And so then our known rates are the rate, which is in 4.5 cubic feet per minute. That will be my volume. dV dt is 4.5 cubic feet per minute. And my want would be rate of change of radius, which is dr dt. And that's what we're trying to find. We also want to know what is the rate of change of the radius when radius is equal to 2 feet. So that's also our known. The equation we want to use is the volume. So here's the equation. Is the volume of the sphere, which is 4/3 pi r cubed. Volume of the sphere. Now we are going to take the derivative implicitly with respect to time. So volume, derivative volume is dV dt. dV dt is equal to 4/3 times pi times the derivatives, which is 3r squared, times the derivative radius with respect to time, which is dr dt. Now we can simplify, so dV dt is equal to 4 pi r squared dr dt. Now we're going to plug in our known and solve for our want, which is dr dt. dV dt is 4.5 equals 4 pi, radius is at 2 squared, and we're looking for dr dt. So 4.5 is equal to 16 pi dr dt, and then we're going to divide by 16 pi. So then dr dt is equal to 4.5 divided by 16 pi, which is, I'm punching into my calculator, and what I get, the radius is changing at the rate of 0.089 feet per minute. So this is an example of related rates.